with the other countries. We also initiated this Air Quality Management Association. We started this in 2022. The main objective of this Air Quality Management Association is to enhance the understanding of the science behind air quality by promoting knowledge of clean air and understanding best work practices. The AQML was formed to address the issues of ambient air quality, indoor air quality, health risk, technological interventions, and policy formulations. So AQML facilitate young professionals to contribute towards advancement in the field of air quality. Next. So as mentioning to you, the CEPHA network, it was a UKRE funded project. So the idea is intersectorial, interdisciplinary that will help provide multiple health, environmental, and socio-economic benefits. Next. So we also started an air quality management. We call it as an Indian International Conference on Air Quality Management. So it is every year in December it will happen, and we successfully completed last year. And so you can look at the more details about this conference in the ISACAM website. Now, I'm heartily welcome to Dr. Rakesh Hooda. He's a senior principal coordinator, Indo-Finnish Research Corporations. I'd like request Lakshmi to introduce Dr. Rakesh Hooda.
Dr. Rakesh Hooda is an experienced scientist with over 22 years of expertise in sustainable ecosystems and air pollution climate interactions. He specializes in climate research, aerosol processes and phenomenon studies, emission inventories, cryosphere research, and sustainable development. He has led and collaborated on numerous international research projects, and his work spans both ground-based and Earth observation domains with a particular focus on India. Dr. Hooda is also a proficient in leading interdisciplinary teams and has a strong track record in training, mentoring, and science communication. His current position is Senior Principal Scientist and Coordinator, Indo-Finnish Research Corporation, Finnish Meteorological Institute. Today's talk is titled Climate Change and Air Pollution, Complex Interactions from Local to Regional Scales. We welcome you, sir, for the talk.
Thank you, Lakshmi. Thanks a lot for this opportunity. And first, my apology to have this last change of time, and but somehow we managed to make it today itself. That's a good signature for me. So I will start with this talk basically, and I will speak primarily on okay. Let me share my screen. Oh, is it visible now? Hello? Is it visible?
Yes, sir.
Yes, it is visible.
It's visible, clear.
Okay.
Maybe you
Okay.
can go to presentation mode would be better. I think in my screen
Yeah,
is
yeah.
showing still.
Sure, sure.
Yeah.
So is it okay now? Hello?
It's fine. It's fine. Go ahead.
Okay, thanks. Is it in the power presentation mode?
No, it's not in the power presentation mode. Can you click on the presentation mode?
Just a sec. It's to me it appears that it's in. How is it now? Hello?
It is still in the normal mode. Like that's what we are viewing.
Hello, sir. Can you unshare it once and then when you're sharing, just click share the entire screen. So then we'll use it.
How is it?
Still, we are not seeing the presentations yet. Only the PPT is there, but we are not seeing the presenter view.
Where should I get it? It's already in my presentation mode actually.
So you can unshare it once, and when you're sharing it again, there is an option for entire screen. So we have to click that.
In the sharing mode itself, right?
Yes, correct.
Yes, yes.
Okay. Actually, there is an option for text and images and an option for text optimized for motion and video.
No,
Which option?
Click share sir, from there. Another tab will open. Another box will open.
Yeah.
In that there's
Entire
like window
screen.
entire
Right,
screen.
right.
Yeah.
Yeah. Okay. Just a sec.
You use the entire screen, then it will be okay.
Yeah. Now I got it.
Now you can start projecting your presentation.
Just it's entire screen, but
After
are
sharing
you able
the entire...
to see something?
No, it's coming.
Yes.
Yeah.
Good.
Please go
What
to your
are you able to
presentation
see
slide.
now?
We can see your WebEx window.
Sorry?
So we can see your WebEx screen.
Now
so you can go to your presentation.
Minimize the WebEx this thing and only start presenting with your you open your presentation.
Okay,
You open the
just a
presentation.
sec. Yeah. How is it?
We can see, sir.
Okay, please go ahead.
Okay, thanks. Good. Thanks for the support. Actually, we are mostly used with the MS Teams, so fine. Right, and I will talk on this climate change and air pollution. And we do know that these two different components have a very complex interactions when we see it from local to regional scales. And with this introduction, I will go with what's the outline of this this talk today. I will cover in. We do know that this carbon dioxide is one of the most recognized gas, and which is having highest radiative forcing. But beyond CO2, what are the different air pollutants or atmospheric aerosols which they have equally pretty important in terms of both climate change and air pollution? And in addition to this, I will also cover on air pollutants and climate. Basically, in these aerosols, there are many substances which are present in the atmosphere, and those have very much deterioration of air quality and human health, and these also contribute towards the climate change warming. So these different air pollutants have very much interaction with the climate. And within all these different perspective, I would also look into give some insight on what are the different processes and phenomenon which makes this air pollution and climate as a very complex interaction, and that leads into having very negative effect which depends upon some time scales, and also having a some spatial variability in these different interactions. And towards the end, we can propose some what should be the way forward in terms of taking this complexity of air pollution and climate change in an optimized way, and what is achievable basically. So this is all about today's lecture I wanted to deliver in. First, if we start to what's are the kind of driving factors, or what are the contributors to this grand challenge, and what are the kind of nomenclature in general understanding of these different challenges. And we do understand that if naturally there is a greenhouse effect, and without hello? Is it okay? I'm
1 minute. Swaroop, just look at it. Please, all of you unmute except speaker, please. Thank you.
Thanks. Okay, so as we understand that there is a natural greenhouse process in the atmosphere, and without it, this greenhouse effect, the temperature could have been minus 18 degrees centigrade. But now we do have these different challenges, or these different components in the atmosphere, and that's what we do have some temperature in positive. And generally, if we say spatially, it could vary between different degrees, but say 14 degrees centigrade if it is. But we understand that if this is a kind of pre-industrial time, or before these anthropogenic or other sources of emissions, there could have been some variability in this temperature. But now we do understand, because of this rise in temperature, there is a climate factor which is changing, but how it is changing. So to address these grand challenges, primarily for today, I will address this climate change and air quality. But in addition to these, this is a kind of very complex process in the atmosphere, where we have different sources, and there are indefinitely implications of these different processes, and there is a feedback loop of these different components in the atmosphere. But why this climate change and air quality getting a kind of very complex interaction, and it depends upon on very much on spatial variability, and because of demography change or population or urbanization, this change from one continent to another continent. So to address this problem, we do need to have a discipline of a different or multidisciplinary approach in understanding all these complex processes, and we do need to have a kind of integration from expertise of natural sciences or social sciences, medicines, technology people should be there. And also we do need to have for having these ideas, but for implementing our understanding in experiment, some observations or some understanding of the field activities. And definitely after having this understanding of science, we do need to make this science diplomacy also, and there should have some very broader network globally to address this problem, because this is not pretty much local, but it travels through local to regional and having impact as global scale as well. So if we see this climate change and air pollution, we do understand this climate change intricate relationship with air quality. That means that these two environmental forces having a complex interplay with each impacting the other. So this is a kind of broader perspective, but thus far it's mostly the understanding is that the air pollution as a driver of climate change, we often think in our research community. But there is advancement in the further understanding that this air pollution as a driver of climate change, but it's vice versa also. So it means the changing climate can also drive this air pollution in a feedback loop. And through this semantic, it is elaborated in that sense that if we have this climate change, and at a synoptic scale, we can understand that if we have this climate change possibilities, then there are more extreme weather events, and that leads to rainfall anomalies, strong winds, dry lightning, and high temperature. And also because of these, there are high probability of having longer wildfire seasons or forest fire. And this intensive increase in the wildfire and also the intensity, that further leads to, again, in terms of disturbances or changing in the biomass, thawing permafrost, and direct carbon emissions. So that leads into that way. And if you see on the left side that all these different component, they leads into greenhouse gas emissions and also the ambient air pollution. And further, if we close this loop, these greenhouse gases, they further implicate towards the climate change or increasing the synoptic scale temperature, or having anomalies in circulation pattern or relative humidity or precipitation, etc. But this is a kind of different perspective. So in today's lecture, I am not spending much time on understanding these extremes, but I take this opportunity to introduce that here at IIT Madras, we are hosting this symposium of 3 days in February, and there we'll deal with in a very comprehensive way how these ultra-fine aerosol processes and numerical modeling of urban climate extremes. So we wanted to give more a sense how these atmospheric aerosols have implications through the modeling, and we lead towards understanding these urban climate extremes. So, but leaving apart this climate change, air pollution in this scenario, I will jump to very conventional approach. We do understand in our fraternity that this climate change and air pollution, this is primarily derived through the emissions, and these emissions in the atmosphere, they by and large are in anthropogenic nature or natural, or mostly it could be forest fire events also. So primarily these are the major forces of changing in the climate. It has a feedback loop with these emissions in terms of temperature, precipitation, and circulation pattern also in meteorology perspective. And if you see these all three major components of emission as a source, they also lead in the atmosphere changing in the atmospheric chemistry, and with these different aerosols or different components, they interact with each other under different processes, and there is a change in the atmospheric chemistry of many of these different components, and that leads further towards the air pollution. So if there is a single component which we'll highlight in the following slides, but just for understanding that the main driving force in the conventional approach are the emissions, and they have a feedback mechanism with the climate, and because of direct emissions have change in the atmospheric chemistry as a precursor, and because of different climate variables, it has very much transformation or physiochemical transformation takes place in the atmosphere, and which that leads to the air pollution. Because of all these changes in air pollution also, we have different components, not only the PM particulate matter in different aerodynamic size, but it has very much chemical composition also, and that chemical composition or that nature of toxicity, it depends upon mostly on the atmospheric processes. So through this, basically giving this background, first time in Europe basically, or globally as well, under this European project UCARI, where India was also one of the partner for the pan-European emissions. In addition to the particle mass emission inventory, which is very conventional approach and people mostly rely on that, but we do have very scarce knowledge on the particulate or the atmospheric aerosols or the particle number emission inventory. So particle number inventory was the first introduced in 2010-11, basically under this project as a pan-European activity. And what the kind of under having different assumptions of chemical composition, density, and shape of the particles, and also the source type, the estimation depending upon this size resolved particle number inventory, there was estimation of ultrafine particle emissions as European continent. And but from this, the most appealing or most understandable outcome was in terms of that, based upon this particle number inventory also, the road transport and other transport sector were the dominating factors basically, and considered as primary anthropogenic particle number and ultra fine particle emissions. So in line of this approach, which was adopted in early 2000 2010. In India also, under a bilateral activity, basically, there was an attempt to having, at least from the transport sector, to estimate these different emission factors, because the emission factor estimation is the first activity. Basically, in addition to collecting the activity data, you need to have emission factors. Then you can calculate the total load in terms of some number per kilogram. So that is the emission inventory. So for this particle number emissions, this activity was conducted for the road transport, or primarily we adopted this driving cycle of Delhi bus, and there was a chassis dynamometer tests were conducted, and there was a very much setup of advanced instrumentation and to consider this particle number, concentration, size distribution, chemical composition, and also the equivalent black carbon mass concentration. We had CPC, and also with a cutoff of 2.5 nanometer, which is written over here. Also based upon those observations, we calculated different emission factors to estimate the particle number concentration for different regions. And we also used very nano size particle concentration or particle observation instrument, which is called electrical low pressure impactor. And also for the chemical composition, we also use this time of flight aerosol composition, chemical speciation monitor, TOF ACSM, and ethylometer for equivalent black carbon. So this was some sort of setup at Indian Oil chassis dynamometer facility, and a team from Finland. We had a couple of months activity for estimating these emission factors for the vehicular composition. And so if you see this plot, basically we estimated for different types of fuels, and these are on the y-axis, these are the emission factors. And if you see these histogram, this blue one is primarily for the European fleet, which is having a cold start, and this fresh, and also again fresh. So this fresh indicates that these are primarily the exhaust particles or exhaust aerosols. These are containing the particle mass which is formed from say nucleation or condensation processes, and we labeled these as a fresh emissions, or we can say naturally, which is coming from the tailpipe. And these are the real world, we can say, fresh exhaust, which comes under dilution and cooling and subsequent particle formation processes, and directly coming to the air. So these we consider as fresh. And what do we mean by primary? So we also took into account, because this was primarily for the particle phase. So, and we put thermal denuder to evaporate this semi-volatile organic compound. So those particles which are having non-volatile fraction of particles are considered as primary particles. So under this setup, basically, we, in addition to estimating the emission factors, we also came with very much insightful results, which showed that in India, by that time itself, it was a kind of leapfrog from Bharat stage 4 fuel to Bharat stage 6. So this was a kind of understanding that using these different fuels also, there was a reduction in particle number as well as the equivalent black carbon from heavy duty diesel vehicles in India. So this was a very promising understanding for us as well. And in addition to this, since it was a research study, we also try to use, in addition to the lubricant and fuel make a kind of different combinations, we also concluded that it's not always a good scenario in terms of reductions if we keep one constant element and we vary the other one. But the best scenario is that when we change both lubricant oil and also the fuel, then we do have very positive or very substantial reduction of particle emissions. So this study we conducted back in 2019-20. So this gives some more understanding in Indian scenario also, that how the particle number emission inventory is important in addition to your particle mass. Okay, so this was thus far in terms of composition and size, but we do have, in addition to this climate change and air pollution, there are health implications also. So in this three-dimensional way, if you wanted to see that how this air pollution, climate change, they have an interaction, and that leads to the health implications. So if we start that there's air pollution and both particulate matter or ozone or other variables which we inhale directly, and from this air pollution activities or from these different sources, as we discussed in previous slides, that on sectoral emissions, there is a greenhouse gases release also, and that leads to the climate change. So if you follow this path, so we also understood that in addition to direct inhaling of air pollutants, there is a process of climate change that worsen the health impacts of air pollution. And if we go by this loop, basically, we do understand that how there are different climate change variables which make this very worsen implication on health from these air pollutants. So we can name few of them, say heat waves or ground level ozone, which is a secondary pollutant which comes after having reactions in the atmosphere. And of course the particulate matter, again, in addition to having this direct, but in the following slides we will discuss about it in depth, that how these particulate matter having a change in the atmosphere due to different other variables, and directly because of change in the climate variables, there is a intensity enhancement in the wildfire smoke, and again there's a health impact which exaggerated because of these things, and all this results into hospitalization for heart and lung diseases. So that leads into a kind of loop, basically, how these air pollution and climate change variables get interacted and worsen the health. But the good thing is that at least that we can protect this health by implementing climate and air quality policies. But before that, we do need to have a comprehensive understanding of different processes which takes place between climate change variables and air pollution. Okay, now if we see that emphasizing on atmospheric aerosols or particulate matter, which is one of the prominent variable in our scenario, which do understand that because of this there is a health degradation, because of this there is a change in the climate change, there is a we can say anomalies in the climate change scenarios. So if you see in this figure, if you see y-axis and x-axis, basically, so in y-axis, with this color code, we are highlighting that the primary aerosols and secondary aerosols. So at the bottom, which is primarily, we can say, representation of a secondary aerosols, and which is having a high magnitude for say biogenic emissions or vehicular emissions towards the secondary aerosols, and biocombustion somewhere in the mid, which is coming under primary as well as the secondary aerosols. But from the top, if we consider which are the primary aerosols, mainly the mineral dust or the sea salt or primary biogenic aerosol particles. So to distinct that which are the primary aerosols and secondary aerosols and how they propagate as time and space depending upon different processes, that is depicted in this slide. And we wanted to consider that what are the sources and processes affecting atmospheric aerosol composition from near source to the continental side. And in x-axis, if you see this in between this green and the gray size, gray color, basically this green color, it reflects this importance of particulate material relevant to gaseous precursors, which is given in this green color. So because we do understand that gas and particle phase, so how that get transformed within each other with different processes. And at source, if we see over here, at source, different processes are taking place. By name, we can say the gas oxidation, condensation, or aqueous phase reactions, or nucleation. So these processes, which are in seconds, basically taking place at the source, and then they liberate towards having implications at the local scale, and then also with aging processes, they lead towards the regional implications. And furthermore, if you see, they lead further towards the continental side. So with time and space, all these different, we can say, precursors, they took different dynamics in the atmosphere and getting in form of implications at the continental level. And finally, if you see that the journey ends at wet deposition or dry deposition. So this is all about how these different sources they are emitting, and with the temporal and spatial variability undergoing different processes. So, but the highlight from this picture, I want to show that there is a dominance of secondary aerosol, which is across broad spatial scale, and there is a local importance of both primary and secondary aerosols. So this is a kind of message which we got, that in the atmosphere, primarily we can say the secondary aerosols are more implicative in terms of implications towards air pollution scenarios as well as climate change. So if we see in a broader perspective, and again from this UCARI study, there was thematic, and there was a very in-depth discussion that how these molecular scale processes have implications with the global scale. So if, as we just very brief hinted in the previous slide, that at the first, in the second level, we first need to understand different processes, which could be through modeling, but those models are at the nanocluster level or the process modeling. So first we need to start understanding of different processes in which takes place in seconds and which is at micro scale. And as we go further towards expanding the time scale, we need to have further more activities to close this loop in terms of, say, laboratory or chamber experiments. And also, again, we need to, we can cover up with the advancing the instrumentation technology for advancement or enhancement of observations, and we can conduct this measurement campaign, and then we can come out with these Lagrangian modeling, and we can couple all these process level model activities plus observations as a validation. We could have remote sensing data also, and then with these three different understandings, we can lead out towards global chemical transport models or regional chemical transport models, and that leads further to establish this global climate models. And but for all these activities, we do need to have some long time measurement or observations to validate these models. And the ultimate nowadays, the work is on how we can integrate different landscapes or different spheres to come out with some integrated Earth system. So this loop goes, or the research chain which is connecting from molecular scale process to global scale passes through three key objects or three key components, basically this integrated measurements, modeling, and before that we need to understand the theory, which is through the process modeling approach. So this gives an idea that how this interaction taking place from local scale to the global scale, and different components, how they are interplaying each other. Okay, then we do understand that what is the importance of different processes, and these processes we can understand size dependent, because we do know that this primarily from health perspective, there is a more emphasis on particulate matter mass, which is primarily PM 2.5 as an cutoff size aerodynamic diameter, which we use as having established implications towards the health. But if we leave apart this health aspect and we focus on air pollution and climate change understanding, then we do need to go back to very nano sizes, and these different size dependent dynamic process, they govern this aerosol number as well as the mass loading. This we can see from this that if the in the blue line basically and the legend which gives an understanding that this number concentration or number size distribution, which is per unit of centimeter cube, and there are different processes and different sizes which are taking place. So in the blue, which is showing us the number size distribution, and in the red we are more towards larger size particles, and that shows mass size distribution. And if you see kind of subset of this figure here, you can see further down that if we start from the cluster mode, which is up to 1 nanometer size particle size, and it has a kind of positive or negative feedback mechanism when it gives a kind of different scenarios in terms of these nano clustering, or how there's a growth in the size of different molecules taking place. So we do have around 1 to 3 nanometer. We consider this as a cluster mode, and afterwards we do have, depending upon the size bins, we categorize that up to say 25 nanometer, we can say this nucleation mode. And then we have this Atkin mode, or accumulation mode. But the story starts from here for the mass basically. So you can understand that even before our particle mass, there are different things which are taking place before we lead up to this particle mass. And then we have this above 100 nanometer, we have considered this accumulation mode, and again above than that we do consider
I'm
say
not seeing your presentation.
Sorry?
Presentation is not visible.
Sorry? Hello?
1 minute, 1 minute. Can others are seeing the presentation?
No, sir. Screen is not coming, sir.
Screen is not visible. Can you please share it again?
Screen is not visible.
Yes.
Since when?
Maybe last 2-3 minutes.
Really? Oh my
Yes,
goodness. Oh. Is it now? Hello?
Yes, sir.
Is it
now
now?
it's fine. Yeah, it's fine.
Okay, so where I was, sorry, you should tell me that, but on my screen, I didn't get any message actually. Okay, so where we were, should I repeat something or it's okay? Hello?
Sir, from this slide only, sir.
Oh, from this slide only. Okay, thanks. Okay, so I can start from the beginning. Basically, in the previous slide, we did understand that there are different processes taking place at very seconds level, and also in very much in the spatial, very much in the local perspective. So in this slide, we wanted to understand that in addition to this particle mass, if we go further down to nanometer size, there are size dependent dynamic processes which those covers aerosol number and mass loadings. And if you see the subset of this figure, we can start from the size of 1 nanometer also, and in 1 nanometer to 3 nanometer we consider this as a cluster mode, and 3 nanometer to 10 nanometer we do say that it is a nucleation mode, and from less than 25 nanometer around it's a Atkin mode. But it depends upon the size, means how we work on this, but by and large this is the kind of we can say the size distribution of aerosols in atmospheric aerosols. And then we do have this accumulation mode and coarse mode. So you can see this story of particle mass. It starts way after having many other different processes. So in this figure over here, if you see this blue and red, and blue, it shows the number size distribution, and which is having a unit of per cubic centimeter, and we all know that mass size distribution, which is in volume, and we do consider this microgram per cubic meter. So if you see in this figure how we starts with different processes, and if for number size distribution, you can see that which are the different processes, those are affecting this total number concentration. So in this, we have a positive feedback from, or positive contribution from in situ new particle formation. If we have primary emissions also, and but there is a squelching also, or there is a decrease in the particle number because of the coagulation and deposition processes. And on the right side, if we understand the same processes for mass concentration, we can see this again, this primary emissions have a positive, and then both this condensation is positive but evaporation is negative, and again this in situ new particle formation that takes place, that gives you enhancement in the mass loading. And then with the deposition, as we will see in the next, wet or dry deposition, which leads into the decrease in mass loading. So I'm trying to explain you that in addition to this particle mass understanding, we do need to consider this number size distribution also, and then how size dependent different processes are existing in the environment. Okay, so based upon these previous slides, basically, so now we can see before jumping towards the control scenario of particulate mass. If you see what is, so this is a kind of overview. If you see, if you wanted to fix this, so my slides are visible?
Yes, sir.
Okay,
Yes.
so please interrupt whenever it's invisible. Okay, so we can see this smallest particles matter. So it's not only PM 2.5, but way before even PM 0.1 microgram per cubic meter. There are number of different processes which takes place, and that leads to that problem basically. So if we wanted to have a very comprehensive understanding of these different controlling strategies, we need to understand from the bottom basically. So if you wanted to fix this mass, which is say around 0.1 micrometer, I can say, for this itself we need to start from bottom. And you can see with the time stem and also in diameter how these say 10 nanometer, 1 nanometer or 100 nanometer it's different processes are taking place. So at cluster level, we need to have this new particle formation. So, but up before that, I can say that these are the smallest particle. So these are having a very substantial role if you wanted to consider a very comprehensive strategy. But please keep in mind, out of the air we breathe. So these different processes, these are not very much directly implicating us in terms of what the air we breathe, but there are different processes which leads to those size of the particles which are harmful and which we inhale. And those small particles, if those are not very much in primary in nature and secondary in nature, those are coming from these different processes. So unless, as we have seen in the previous slides, that these secondary aerosols are pretty important. So if we give this start over here, that these different molecules in terms of new particle formation events, basically we do know that we do need to have these sulfuric acid as a nuclei basically to start this. But on top of this, we the recent work, it gives an idea that for this heterogeneous nucleation we can have this ammonia and dimethylamines also. So once this cluster is formed, then it goes to further growth basically. And then for this growth enhancement, as the time passes, there are low volatile organic compound and as well as nitrate in the atmosphere, and that leads to give this large size in terms of size distribution enhancement in the size of these. But the overall understanding is that in the environment or in the atmosphere, the particulate matter which is present is having a more than or about 80 to 85% is secondary mass, and these particles from new particle formation is also having a very substantial role and substantial contribution. It goes up to 65%. So this is all about a kind of a holistic view, how when we reach to these mass, how these different processes are taking place. Okay, so what is needed to understand these processes? We do need to have a very comprehensive observation establishment. And in Finland, since 1990, our leading professor, Marko Kulmala, he has established these observation networks basically, and starting from some basics, and over the time it evolves with understanding or with incorporation. It was started from atmospheric aerosols or from the atmosphere component, but now they have coupled this with the different fluxes from the other ecosystem also. So now they have the understanding of atmosphere, biosphere and hydrosphere, with lakes and with forest and with atmosphere definitely there. And now the to understand these different dynamics in the atmosphere with these different landscapes, they are observing around more than 1,000 different variables to come to this understanding. So I will just give you a hint in atmosphere what all is about, what all are their observations. So primarily the aerosols, atmosphere chemistry, cloud microphysics, micrometeorology, and definitely solar irradiance. And in addition, we do have some synoptic scale meteorology also for this. So, and the good thing is that since it was started now, it has a very important role in understanding in the global dynamics also what different processes are taking globally. And based upon these process level understanding, now there is a development in different scenarios. And this station and also the Pallas station as a GO atmospheric watch system in northern Finland, taken care by FMI, my institute, these are part of many European or global network, and giving the data inputs, and the process understanding and validation of models could be done based upon these different process understanding. Okay, so to next to this, basically in a different perspective, we did understand that these volatile organic compound are one of the most important molecules basically which take part in the growth and leads to enhancement in the size and also coming in form of mass. So these emissions from atmospheric organic compounds and what are the kind of in situ particle formation and growth takes place in the atmosphere. So we did understand that that before this climatic size, which we call this cloud condensation nuclei, and that has a role in the cloud formation, because we do know that for cloud formation, some nuclei or some aerosol is needed always. So in that way, aerosol is a necessary evil. It has very much positive things, and definitely it has negative aspects also. So I mean, through this slide, I can just quickly rephrase the things what we discussed before in terms of different processes and how the loss processes are taking place, and how these Atkin and accumulation mode particles, they are considered as background aerosols also. So this is the thing basically which we face in our conditions, that uh, we can put many strategies for controlling this particulate mass, but already we do have this background concentration of aerosols which is very high, and because of that, we in ideal scenarios it will be a huge task basically to come to the WHO standards in health perspective because of these existence of background aerosols. So if we discuss in primarily that from the source, if there are volatile organic compound or primary organic aerosols are taking place, so based upon these organic emissions, there is these ultrafine aerosol source which are coming from nucleation activity, and then this is of say size of 1 nanometer and 10 nanometer and 100 nanometer, which we have seen in the previous slide also, and how these different processes are taking place in form of because there are simultaneously there is a condensation and coagulation processes which are taking place, because in condensation there's a growth is taking place, but in coagulation we have some sort of squelching also for some of the particles, or removal of these, or losses of these particles or the molecules basically. So we can see that from traffic transport or from the biogenic sources, these organic emissions are taking place. And as we have seen previously, there is this cluster or nucleation processes which are taking place. There is a further growth because of these VOCs, and then we do have some more condensable vapor sources which are coming. When these molecules comes in the atmosphere, there is an oxidation process, and then further growth is taking place. Then afterwards, when we do have this much size of 100 nanometer basically, then these are having a because further to go to this cloud condensation nuclei, you do need to have some favorable conditions in terms of relative humidity or supersaturation condition. So every aerosol doesn't go further to act as a cloud condensation nuclei. So those remaining one, they creates this haze and background aerosols in the atmosphere. And these aerosols basically, we can consider this ultra-fine aerosol in the atmosphere, which acts as a sink also for fine aerosols basically. Because of this coagulation, that's what these particles doesn't go further, but they get transform into this background aerosols, and which is considered as a fine aerosols around 0.1 micrometer size, and these are named as background aerosols basically. So as we have seen that afterwards, when we reach this 100 nanometer size, when they are in form of clouds basically, then this is the wet deposition pathway. And this, as I mentioned just before, that it depends upon the composition, size, and relative humidity, and that influences the water uptake by these aerosol particles and reaches up to critical size basically, and acts as a activated nuclei for cloud droplet formation. So this is all about different processes and how there is a squelching, and that doesn't go further but leads into form of ultra fine aerosol sink, and that translates into fine aerosols. So this is the kind of entire process which leads into both CCN size particles as well as the fine aerosols. Okay, as we have just elaborated what's this CCN and how these clouds are making influence on the climate perspective, you might have already aware with these different interactions. And primarily, if I just rephrase these two major things, one is aerosol radiation interaction and another is aerosol cloud interaction, and it is named with the scientists also this indirect effect, which is nowadays we call it as a aerosol cloud interaction. Basically, these indirect effect we can say aerosol cloud interaction, and this is direct a kind of incident radiation aerosol radiation interaction. So in this aerosol radiation interaction, it depends upon what's inside there in form of aerosol, whether it is scattering in nature or absorbing in nature. So here the aerosol, they scatter and absorb this solar and thermal infrared radiation, and it alters the radiative balance of the Earth atmosphere system, or equivalently the planetary albedo. So it changes the surface albedo situation in atmosphere, or make a kind of Earth energy budget alterations because of this, majorly because of this. But climate perspective, the more important is nowadays, because that this process is with high uncertainties, and that leads kind of uncertainties in the estimation of radiative forcing for different aerosols when they are interacting with the clouds, because that changes the properties of the cloud. So here the aerosols, they modify these microphysical properties and the radiative properties and lifetime of clouds, and that alters the radiative forcing because of these different processes. So this is all about the next step after this fine aerosols. Okay, so just to give an idea, what is this cloud condensation nuclei generally?
Rakesh, can you hear me?
Yeah.
Yeah. How long it will take to?
Maybe another. How much time we have? 15 minutes?
10 minutes? Yes, within 5-10 minutes, 15 minutes. Okay.
Okay, I will just
wrap
it up. Okay, so in this cloud condensation nuclei, if we see this size of this cloud condensation nuclei, this is typically it's a size in 50 to 400 nanometer, and as we have shown that under these favorable conditions, it translates into cloud droplet CDC basically, and condensation, cloud droplet condensation nuclei, and this size is 5 to 50 micrometer. But the good thing to understand over here is that these cloud droplet number concentration, these are taken into the climate models, and the modelers, they generally take the outer band of this cloud droplet number concentration, and that gives a huge uncertainty in terms of estimation of this indirect effect. And from this, it varies from say this minus 1.9 to minus 0.6. So this is the kind of band or the range basically which gets affected because of this band selection. Okay, so this we have seen already in the previous slide. So those fine aerosols we can consider as haze also, and as we have seen, this haze formation is taking place before this the particles which goes to CCN. So again, the composition of this haze is coming about 80% for secondary mass and about 65% for new particle formation. So To enhance this understanding of this haze and CCN, so we are starting our activity in India also, and we wanted to understand all these feedback mechanisms and going up to sub 30 nanometer size, and to understand these CCN and haze perspective in two different environments in India, and to understand these different precursors. So in Indian scenario also, we are starting this study, and which will end up in 2028, and these are the different institutes who are taking place, and Chennai is one location, and also in IGP we are working together to understand all these more or less the same processes which already I explained, and how these ultra fine particles, they are also acts as a decreasing agent for these fine particles. So decreasing, but in the strategies basically, so decreasing fine particle emissions can accelerate this NPF and secondary growth. Okay, so apart from CO2, this black carbon also very much important, and this black carbon also have not very much health impact, but in climate perspective, it get in the interactions with the cloud, and also having direct aerosol radiation inferences also, and through cloud also it has inferences, and this is the second most we can say radiative potential component in the atmosphere. But because of this short life, it is very much achievable to control this black carbon. So here we show that how these black carbon have spatial variability, and where in global perspective having highest impact, and because of this different processes, we can say that it originated from somewhere but have impact globally somewhere else because of these different processes. And with BC we have these cooling agents also, and which we saw that it compensate the radiative potential of black carbon because of this organic carbon stuff, but that is always not true. Okay, so to understand this perspective also for our Indian Himalayas, because if you can see in the previous slide, this is the hottest area where the Indian Himalayas or the glaciers are very much prone basically, in addition to Arctic, which should be studied further to understand all these different processes. So again, with this EU Horizon project, which is starting in February and ending in 2029, we have a consortium of 9 countries, 20 partners, and more than 60 researchers, where we will again understand different processes, and IIT Madras is again involved in this study from the Indian side, and we will understand different processes, modeling, and impacts in this cryosphere, atmosphere, and hydrosphere landscape, and we will come out with dissemination and some strategies how we can control this. So in this slide we are just spatially distributing which are the study sites across different continents, in Arctic, in Alps, and in Himalayas. So this is overall different work packages we are covering with the different components, observations, modeling, impacts, and knowledge sharing, and how it is varying from local, regional, and global. So these are the composition where we are again starting from the process understanding, coming out with different process models, and then also leading up to our system model or emulator generation based upon these process understanding. And also we are catching up on different hazard understanding, or how we can generate different scenarios, say glow, drought, or flood situation. So what should be needed basically for this understanding in a comprehensive way? We do need ground-based data, satellite, and multi-scale model, and how to assimilate different informations starting from empirical understanding, and how different strategies could work. Again, since we do know that organic compounds in the atmosphere are the prime one, I will just take 1 minute over here that these in the atmosphere, because of these different emissions, be it from biomass burning or transport, we do have this volatile organic compound, and these are acts as a precursors for secondary organic aerosols, and these are having this one volatility, which is the highest one, and then we have this intermediate volatility, and these are the primary organic gas. When they release in the form of molecules, once in the atmosphere, they get this mechanism of evaporation, reaction, and condensation, and that they leads into the form of, say, secondary or primary organic aerosols. So through our research also, it is an understanding now that in particulate matter, this is the major component basically which is working, but still we do need to have much more understanding, because we don't have that complex understanding thus far, that so the mathematically we can intervene these into the climate transport models. So still the work is on. Okay, so based upon these VOCs and then chemical transport model in FMI, we have this CLUM air quality assessment model. And these are the different tools basically we are utilizing in terms of giving this product. And from FMI, it has been optionalized at India Meteorological department also. So IMD site or IMD is using for their operational purposes now this CLUM from FMI. Again, as I just explained you that these biogenic volatile organic compounds, how they are leading a very much substantial role and having a very complex nature in terms of understanding or interactions with cloud condensation nuclei also. So still the work is on, and we wanted to decrease the or minimize the uncertainty information of these chemical transport models and how this radiative forcing estimations could be improved. And in addition to this CTM, now in FMI, the progress is also towards this EC-Earth-4, where we are incorporating these different organic aerosols. And now this under EC-Earth-4, we are also incorporating this ocean and ocean biogeo chemistry in addition to these atmospheric or atmosphere or land or sea surface changes basically. So what are the challenges? I will just give a kind of very much heading that there are some inadequacies of traditional secondary organic aerosol formation models, as we already discussed, and the health impact of PM 2.5. We haven't yet for understanding of which single component or single pollutant having very much harmful, which is the harmful most harmful factor in the PM, and how these linking chemical constitutes to health effects also still in form of peroxides or radicals. We are not having much understanding of the toxicity, and focus on a holistic approach that can integrate observations of this gas and phase gas and particle phase particle phase molecules basically, which are in the atmosphere, and these could be improvised through microsensors or hybrid model techniques. And then we do need to have a kind of very optimized emission reduction strategies, because as we do understand that minimizing one can increase the other pollutant implications. So this is primarily my last slide. Basically, if we take the base of this climate change benefit and a climate change determinant, there should be have a kind of win-win situation. And with these two different scenarios, we can understand that sometimes this air quality improves, or other time the air quality declines also. So with these net zero emission strategies, we need to be very much careful. Okay, so this is the way forward basically. Again, just we'll go through the headlines only. The challenges in Earth observation there are, because these are very much ground stations or localized, but we do know that satellite cannot cover everything. So for ground truthing or the model validation, we do need to have this ground observations also. So what are the kind of current monitoring gaps basically we do have in terms of different processes understanding? So these are established with some specific goals, but they should have some holistic approach in form of different network, likewise smear 2 station, and how we can enhance this global coverage in understanding these different processes. So ultimately, then we can only come out with some policy approaches, or at local as well as the global level. So this is all about, I think it took a lot of time basically to deliver this, but if we have some time for discussion and question, I'm open. But I'm still here. If anybody interested to interact, I'm sitting in 344 here. Hello.
Hello. Yeah, thank you, Rakesh. So very nice presentation. You covered a lot of details about the interactions between climate and air quality. So very nice. And you also work with an institution which is develop several models connecting from air quality and meteorology. So we're just to try to look at it from the understanding the climate change air pollution relationship. So we've only now our major focus is only on the particulates pollution. Although you have mentioned about there is a possibility of secondary aerosols or other pollutants which are contributing to the climate change aspects. In that context, so what are the emerging pollutants you feel that we should start focusing in terms of measurements?
Yeah, primarily, if straight I can answer, these are the organic aerosols. Basically, we can start with that, though we do know that there's a very much big mass spectrum for coming out with these different volatility organic compounds. But if we start with the with extremely low volatile compounds or semi-volatile or intermediate volatile compounds, that will lead into much more understanding that how there is a growth taking place, and these are having much more contribution to particulate mass. So this is one emerging thing, and then based upon this only, because this is the aspect which is lacking in the models also, or in the estimation of the radiative potential as well. So this is one domain basically, in addition to black carbon or brown carbon.
Okay. And this FMI is very famous with developing models, particularly with meteorological interactions to the air quality. So in that context, what is the latest, where, because in India, we always use the EPA models, but even in the research, sometimes we used to use, but the use of FMI based models developed by that organization is not very popular these days. So is there any comparative in terms of some limitations, or there is a new tool that is available and will be useful for research students to use it?
Yeah, surely. I think this CELA model, which is a chemical transport model, which I depicted in one of the slides. So it has been operationalized in Indian conditions also, and now still we are improvising it because this is the one of the most acceptable chemical transport model in the European continent, and we started with the Indian scenarios also, and now we are improvising it because the conditions are different in terms of meteorology, in terms of that the kind of extreme events, also in terms of high loading during this post monsoon season. So when there is a transformation into from very low aerosol load to high aerosol load, so that is the thing basically we are working on. And of course the emission inventories, we do need to work on very much in a comprehensive way to understand the dynamics of this real-time emission inventory. If we can improvise it, and also the particle number emission inventory, we do need to understand that also, in addition to our other atmospheric variables which generally we estimate in emission inventories.
Okay. Yeah. And any other questions from any of others who are on the meeting? Okay, so the other things, meteorology in terms of meteorological aspects, like so what is the latest development happening in terms of capturing the meteorological aspects? For example, we always use stability as one of the inputs for our model, whether any such instruments or technology that has been developed or devised to capture real-time stability classes or stability of the atmosphere.
Yeah, that's true. Basically, because you can understand from this MOSM mission also, which recently MOES started, and they wanted to very much comprehensively investing in understanding this micrometeorology, and in a urban integrated system, different vertical profile they wanted to estimate. We don't want to constrain your regional scale models from the global climate model, but if we have some localized observations also of these different micrometeorological parameters, then I think that will be really improvise in form of biases which we are getting in our predictions or in forecast.
Okay. Yeah, thank you very much. Are there any questions from any of you? Okay, if there are no questions, thank you very much, Dr. Rakesh. So we'll just all request all of you to start your camera so that we can have one group photo.
Yes.
So maybe Sarup or Ashwin, can you take a photo? Or Lakshmi? Okay. Thank you very much. Thank you.
Thank you.
Dr.
Thank
Rakesh,
you all,
time
and thanks, Professor Siva.
helping this lecture.
Yeah.
Thank you.
See you.
Bye
Thanks.
all, and
Bye-bye.
see you all in the next lecture. Thank you all for joining the meeting. Thank you.